Good evening. We are going to continue with Chapter 4. And this section here has to do with strong and weak electrolytes. So I hope when you hear the word electrolyte, you're probably thinking of some commercials that you see on TV or thinking about some Powerade or Gatorade to replace some of those electrolytes that you've lost in your body when you've actually worked out hard and sweat and have sweat out some of the salt and stuff that's in your body. So in order to do this, we need to understand the following terms. I'm not going to go in great length with these. You may need to go back and look them up. You can, write in some definitions here. You should be able to remember a solute and a solvent, that a solute and a solvent are the two things that make up a solution. So if I were to quickly just diagram this out for you, and I were to draw a beaker, a lovely beaker on my little bamboo thing. It's hard to draw on here sometimes. So here's my lovely little beaker, and excuse me, I'm going to go ahead and find some water, and I'm going to dissolve some water into this. So I have water in my beaker, and I'm just going to take some plain old salt, and I'm going to dissolve that into here, and I'm going to represent that by little X's. So we have these ions. Sorry about that. We have these ions that are separating in here, and we have lots and lots of space, and so I'm able to create a solution. All right, remember a solution has to have two parts. So the solute are my red X's, that is my salt or whatever substance I have in here that I'm dissolving. The solvent would be the water. And in here, both of these together are going to make a solution. Now it's going to have a certain amount of solubility. It's a certain amount of grams of solute, grams of this that can dissolve in a certain amount of grams of solvent. And then I am going to pull out the conductivity apparatus again in class so you can see what it means to light up the light bulb. There's a little bit about this in the diagram on the next page. But if a current can flow through here, if electrons can be flown through, then you obviously are going to be able to conduct electricity or have a current going through. So electrolytes, they ionize or dissociate. When you think of ionize, it means that they break apart. So they are going to break apart in solution to conduct an electrical current. So if I'm talking about table salt, NaCl, so if I grab another color here, NaCl, we would have the sodium ions and the chloride ions moving independently of each other, as we talked about in the last podcast, that they can continue to move independently of each other until the solution becomes too concentrated. This is ionizing. You put this together as NaCl as one salt crystal, and it breaks apart into sodium and to chlorine once it gets into water, as the pictures you saw from the last podcast. Now, of course, we have some strong versus weak electrolytes. If you think about the light bulb showing or glowing, let's use that word, glowing very brightly versus not hardly glowing at all or not at all. Depend upon the percent of ionization. So the percent of how much of these ions here are going to break apart in solution, which is controlled by bond type and strength and energy changes involved. So let's have, you guys know I'm big on pictures, so we're going to show you another picture of this, and you'll see it in class also. And you can see the extent of ionization. Well, this is showing that the light bulb is glowing very brightly. It's lit up maybe a little bit here, and then not at all with this one. So what you're seeing here, this would be a good example of HCl. You should recognize that as hydrochloric acids. All acids are going to light up a light bulb fairly well. They, especially a strong acid, it fully dissociates. I shouldn't say all acids, I'm going to say strong acids, because the next one I'm going to use as vinegar, which you guys know is a weak acid. And so HCl, you can see that it completely ionizes. I don't have any molecules that are stuck together. It completely ionizes, and so it's a very, very strong electrolyte. There's a lot of charges here, so it has an ability to carry a current. Now this is going to be vinegar or acetic acid. And vinegar, sorry, it doesn't dissociate very much. It actually only a little over 1% of it is going to dissociate. So I have very few ions in here that are going to be able to carry that current. So this would be a weak electrolyte. And then this over here would be an example of sugar. Yes, we know that sugar is going to be able to dissolve in water, but it's a non-electrolyte. There are no ions here. So because there is no ions, I'm really sloppy tonight, sorry. There's no ions, there's not an ability for a current to go through here. So on the bottom of this page here, you have a little statement that Arrhenius' theory of ionization, we're going to talk about Arrhenius again when we go to acids and bases, that the strength of electrolytes is dependent upon the equilibrium that exists between ions and molecules. And equilibrium, we're going to talk about that until we're blue in the face once we get to those chapters. And equilibrium just means that there is a balance. So it's going to depend upon the balance between the ions and the molecules that are there. So again, let's take another picture so you make sure that you have this understood. Strong or weak electrolyte, and how do you know? Well, I would hope that you're saying to yourself that this acetic acid is going to be a weak electrolyte because there's very few ions that are dissociating. And as we talked about, that really only about 1.3% of these actually do dissociate. Over here, this is a very, very strong electrolyte. Let me move this here for you. It's a very strong electrolyte. Hydrochloric acid completely dissociates. And so you can say that 100% of this is going to dissociate. And so it's a very, very strong acid. What does that say about the bonds? Well, what that says about the bonds here is that it's kind of backwards of what you think. I have a very weak electrolyte, but the bonds here are very, very strong holding it together. So over here, I have a very strong acid. If this was hydrochloric acid and you're drinking it, we'd have some trouble and rushing you to the hospital. But the bonds are so weak that the water can easily attract to them and break that bond. So I have a strong electrolyte because it completely ionizes, but very weak bonds. And so it's kind of opposite. Okay, I think that's all I wanted to say on that one. So let's move forward here. So the more ionic in character, the greater degree of ionization, meaning uh, the higher the difference in electronegativity is going to make it more ionic in character. Greater degree of ionization, the light bulb is going to be brighter. The more covalent it is, the more that they are sharing their electrons, less degree of ionization, meaning less separation, less ions, a, a light bulb that's really very low, maybe glowing hardly at all. And then non-electrolytes, that was our example of sugar, substances that dissolve in water but not produce any ions. And remember, we've talked about that like dissolves like. And so like dissolves like, we can say that ionic is going to dissolve ionic substances or in water. And then we can say that polar substances are going to dissolve polar substances and non-polar substances are going to dissolve in non-polar substances. Now, example of a non-polar substance would be like your acetone, your fingernail polish remover. Polar substances would be water, and then ionic substances are like salt. Okay, I think, let's see. I think I'll keep going here. I just have a couple more slides in 4.3. Basically, 4.3, we're going to be doing a lot of problem solving. We've talked about this already. Composition of those solutions. Remember, in a solution, you have to have two parts. You have to have a solute dissolved in a solvent. And when you have that, we can talk about its molarity. And remember, molarity is also its concentration of the solution. And so a low molarity is going to allow those ions to move independently of each other very, very easily. The more concentrated it gets, that's going to be harder for those ions to do that. So we're going to do some example problems on that, and we'll do those in class. And then we talk about dilution. The addition of a solvent, so you should be thinking something like water, to a standard solution to make a new solution concentration. And here's our formula, M1V1. We've had this in the past. Molarity 1 times volume 1 equals molarity 2 times volume 2. And the one thing that you need to remember that I really want you to make sure that you put down is that the moles of the solute before, and it doesn't matter how much you dilute this, is going to equal the moles of the solute after dilution. And so you're not adding any more grams. You're not adding any more of the substance to be dissolved. You are simply adding more solvent. And in most cases, that's going to be water. So the number of moles before is always going to equal the moles after. And how do we prepare this? We did this a little bit last year. You're going to be doing a lot more of this year where you're going to be making your own stock solutions. So if you recall, these are called volumetrics. We're going to use a lot of volumetrics when we get heavy into our lab section. And all of these have a calibration point. They are very, very accurate, and that's where you're going to fill the water line to. So you weigh your amount of solute in the bottom, and you can see that you're going to add some distilled water to this. You're not going to fill it all the way up because you want to have some space to be able to stir or shake this so you can create some agitation and get it to dissolve. And then you would continue to fill up to your fill line, and that would be the concentration of whatever the solution that you are trying to make. Okay, I think that's it. The next page starts the next section, and we're going to hold off on that. So you guys have a wonderful night, and look forward to seeing you again in class. Take care.